Okay, hi everyone. Let's go ahead and get started with today's lecture. Hope you all guys had a good weekend. Welcome to Monday. So today in our lecture we're going to be continuing with the nearest Centroids classifier. And towards the end we'll be seeing a new classifier called the kNearest neighbors classifier. And so let's go ahead and get started. So just a couple of brief announcements before we get started with the content of today. For homework 1, the deadline for that was last Friday, so thanks to everyone who submitted that successfully on time. The grades and the solutions for this assignment we're hoping to get out to you guys by Friday so you can get some feedback on that assignment and see how you did. The second homework will be posted soon. I was hoping to get it out today, but it's looking like it'll be tomorrow. But you've got 2 weeks to complete that assignment. It'll be due in 2 weeks, so not this Friday, but next Friday. It'll be about similar length to the first homework, probably 3 problems, roughly the same difficulty. The first problem on homework 2, you'll be implementing the nearest Centroids classifier on the MNIST dataset. So we covered nearest Centroids last time, and we'll see some more details today. And we'll be talking about this MNIST dataset in particular. The second problem, you'll be implementing the kNearest neighbors algorithm, and we'll be covering that today and throughout tomorrow's lecture as well. So just a little bit of a preview of what the homework problems will be. And then for the third announcement here, I'm planning on sending you guys out a survey, essentially just to collect some feedback from you guys about how you think the class is going and any suggestions you might have. So this will be an anonymous survey. I'll probably give you guys like 1 or 2 points of extra credit if you actually fill it out. But this is just for my own purposes to get some feedback for how you guys think the class is going and how it might be improved. So keep an eye out for this post, probably on Ed. So any admin questions before we get started today? Okay. So today we'll continue with nearest Centroids. We'll see another demonstration of this classifier. After that, we'll go into some more detail about how we actually evaluate classifiers beyond just this accuracy metric that we looked at last time. And then the third thing we'll briefly cover is just an introduction to this kNearest neighbors algorithm. So kNN is it's kind of a simple extension of nearest Centroids, but it actually works pretty well in practice. So we'll get a brief introduction to that algorithm today. Okay, so just some reminders on how nearest Centroid classifier works. What we do in the nearest Centroid classifier is we take our data points and we split them by their class label. So here in our penguin data set, we've split our data points up based on what species of penguin they are. And then for a new data point, maybe this gray point, we compute the distance between each of the 3 centroids and then classify that data point according to whichever centroid it was closest to. I showed you guys some pseudocode in the previous lecture, so keep that in mind when you're trying to implement this for the homework. So let's go through kind of a brief illustration of the nearest centroid classifier just to give you guys a little bit more of a concrete hands-on example of how this works. So let's look at this penguin data set again. And to actually fit our nearest centroid classifier, we're going to be using this sort of train test split paradigm. So we're going to split our data into a training set with 200 examples, and the remaining 133 data points we'll use for our testing set. Here I'm not using a validation set, I'm just using a single testing set, and this is because I'm not doing any kind of model selection stuff. So I'm just fitting one model and evaluating it on this testing set. In fact, I'm going to use just 2 features in my data set just to help us visualize things. But of course, you'll get better results if you use more of your data. And of course, I'm also going to scale my data so that all of the features lie between 0 and 1. And as I demonstrated to you guys on Friday, this scaling effect can have pretty significant impact on your model performance. Okay, so here's my 200 training points. I can find the centroid for each class, which is, again, just the mean of all these data points. I just average them up. And I end up with 3 centroids. But once I have those centroids, I don't even really need to keep my training data around anymore. If I know my centroids, I know how to make predictions. So this is really the training step in this algorithm, is just computing these centroids, and I can throw away my training data if I want. These centroids then sort of implicitly define decision boundaries. And again, these decision boundaries are points that are equidistant from 2 or more of these centroids. So any point on this line has the same distance between the green and the blue point, and so it's kind of the place where my decision is going to flip. This triple point here is equidistant from all three centroids, so I'm really uncertain about how to classify that. But again, the idea is that these centroids kind of partition my data space into three distinct decision regions. So any new data that comes along and lives in this region will be classified as this blue label. Any new data I have that comes along will be classified as orange if it lives in this region, and the same thing for this final green region. Here is now my testing data. So this is the data that wasn't used to compute the centroids. It wasn't used to classify, or rather to train my algorithm. And the data points are now colored by their true labels. And you can see that all the points here get labeled as blue. All the points here get labeled as orange, but we're making a couple of mistakes. There's a couple of blue points in the orange decision region. And so here I'm just pointing out sort of all the mistakes my classifier makes. And if I count these all up, it turns out I have 6 errors made by my classification algorithm. I had 133 training examples in my data set, so getting an error rate of about 4.5%. Okay, so here I'd just like to emphasize that there's kind of 2 distinct steps in setting up our classifier. The first step is actually building our classifier, training our model. And we do this on our training data set. And again, we are just fitting these centroids. But after we've trained this classifier to actually go out and use it to make predictions with it, it's kind of a second distinct step here, where rather than computing centroids, we might have a new unlabeled data point that we want to make a prediction for. It's this red point right here. And the label I predict for that red point depends on what region of this input space we're in and what decision region it lies in. So again, there's 2 steps here, training our model and making predictions with it. Okay, I'd like to introduce you guys now to a fun data set called the MNIST data set. It's a very well-known sort of classical data set in machine learning. It originated back in 1998, so this is an ancient data set by machine learning standards. If you guys have heard of Jan LeCun, a very famous ML researcher, originally introduced this data set. One of the big names in machine learning. But what this data set is it's a collection of 70,000 different images, where each of these images corresponds to a particular handwritten digit. So for example, this image here in the top left is someone drew a 6, and it's got a corresponding label as a 6. This one's a 1, got labeled as a 1. So this is a classification data set with a total of 10 distinct labels, 0 through 9. So a little bit more information here. Each of these images is actually a 28 by 28 image. So it's got 28 pixels long and 28 pixels high. And what this means is that our feature vector, we can kind of imagine taking an image and flattening it out into a big long vector, has a total of 784 dimensions. So this is a relatively high dimensional classification problem. 784 input features is pretty large compared to, say, something you might look at in a statistics class. And so this data set often gets used to sort of benchmark basic machine learning algorithms. It's a nice example of a non-trivial problem, unlike sort of the Penguins data set. In order to sort of pre-process this data, what we're going to do is we shuffle our data. Again, shuffling your data is an important first step before doing any machine learning because I believe this data set is ordered by the class labels. So all the zeros come first, all the ones come second, so on and so forth. So we need to shuffle our data to kind of break that ordering. Then I'm going to use 20% of my data for training and 80% of my data for testing. I think these are flipped. It should be 80% train, 20% test. So small typo here. Okay, so just for some more visualization of what the images in this data set look like, this first row is a whole bunch of examples of images with class label 0. This row is a whole bunch of images with class label 1, so on and so forth. This is not a totally sort of trivial classification problem, because there's a lot of variation in how you could, write digits. We've got like some curly 2s, we've got some flat 2s, we've got some 4s that are connected, some 4s that are not. So there's a lot of variation in the sort of classes here. Okay, so how do we actually represent an image as a feature vector? How do we feed this into a machine learning algorithm? So let's say I've got a digit over here, it's a 1, and it's a 28 by 28 image, which means that I have a total of 28 by 28 pixels. These are grayscale images, which means that each of my pixel values is some number between 0 and 1. A 0 here represents, there's no kind of pen mark, and a 1 would represent a very dark region of the image. So I've got a bunch of zeros in this first row corresponding to kind of all the pixels in the first row of my image. And then I've got some regions shaded in here with the various kind of grayscale values corresponding to this 1's digit. So this is how we can represent an image as sort of a box of numbers. And what we can do is we can take this array of numbers and just flatten it out into a really long vector. So we can take the first row and then kind of just stack the second row after that, third row, fourth row, so on and so forth. And this lets us turn an image, which is sort of a square array of numbers, into just a feature vector like we've been thinking about. Of course, it's hard to kind of visualize these feature vectors as points in some space now because we've got 784 dimensions. Very hard to visualize this. But you can kind of abstractly think of images as just feature vectors like we've been talking about. Okay, so now I went ahead and fit the nearest centroid algorithm on this data set. And what you can see here are the 10 different centroids. So again, we've got one centroid per class, kind of representing the mean feature vector for that class. So here is the centroid for the class 0. Here's the centroid for the class 1, so on and so forth. Okay, and what you should notice is that these centroids are actually pretty blurry. So does anyone have a good guess as to why these would look like blurry digits and not, clean, clear images? Yeah. Well, so are these, but these are pretty clear, yeah? I mean, relatively speaking. So if you compare these images to these ones, these are a lot blurrier. Yeah, another guess. Yeah, exactly. So his answer was it's because we're taking the average of all of our images. So of course, if you average up a bunch of stuff, it's not going to look like any particular thing in your data set. It's going to kind of just look like a averaged out, smoothed out version of your image. So for example, we can look at this one centroid. What you see is it's kind of got a bottom left to top right slant. That's people who draw their ones this way. But also kind of a top left to bottom right slant representing sort of another class of people who might draw their ones in the other direction. So again, these are blurry because they're kind of just an average of a whole bunch of different images, and they don't necessarily look like any particular digit. Okay, so after I fit my nearest centroid classifier, I went ahead and used it to make predictions on my testing data set. What we get here is an accuracy of about 80% on this data set, which is not bad for a pretty simple classifier like nearest centroids on this very difficult problem. So it gets most of these correct, but it's kind of fun to look at where it makes mistakes. So for example, in this bottom left here, this is an image of probably a 9, but the classifier predicts this as a 7. So as you can see, it's pretty hard to do these classifications, even for a person sometimes. And you can see why a classifier might mistakenly label this as a 7. Same thing here, this gets predicted as a 1, even though it's probably a 6. And so in homework 1, you'll be working with the nearest centroid classifier on the MNIST dataset, and you'll actually be reproducing this figure I have on the slide. So, any questions on this dataset? Cool. Okay. So as I've shown you guys, the decision boundaries for nearest centroids in all of these figures are actually sort of piecewise linear decision boundaries. They have this nice line shape to them. What we're going to do next is actually prove this and show it's a fact and is not just an artifact of the data sets we've been looking at so far. So again, my claim here is that for the nearest centroids classifier, it's going to have linear decision boundaries. Let's consider just a really simple case where we have just two different classes and two different features. So a good sort of example to keep in mind is this data set on the right-hand side here, where I've got a blue class and a red class. I fit my nearest centroid algorithm. So this is the mean for the blue class, and this is the mean for the red class. And essentially what I'd like to do is somehow find an equation for this decision boundary between the two. So again, I have two centroids. My first centroid I'm going to call mu sub 1. And this is some vector, some point, that has components mu 1, 1 and mu 1, 2. So these guys here are the coordinates of this centroid here. Same thing for mu sub 2. It's some point representing the centroid of the red class. And these two values, these numbers, are the centroid of this red class. And so to actually find the equation for the decision boundary, what we've got to do is think a little bit about what it means to be on the decision boundary. So a point x, which has coordinates x sub 1 and x sub 2, lies on the decision boundary if and only if it's equally distant between the two centroids. That is, let's say we're working with the Euclidean distance here. The distance between x and the first centroid has to be equal to the distance between x and the second centroid. What we're going to do is we're going to take this equation, analyze it a little bit, and end up getting an equation for this dashed line. So any questions on this setup before we go into the details? There's going to be some math on the next slide, so it's good to understand the setup. Cool. So again, a point is on this decision boundary if and only if the distances between the two centroids are equal. Okay, so in this first step, all I'm going to do is plug into the formula for Euclidean distance here. So nothing fancy happened. I just wrote down what the Euclidean distance is that I showed you guys on Friday. Again, it's the square difference between the coordinates, and then we take the square root at the end of the day. Pythagorean theorem is what you should have in mind here. Okay, anyone want to suggest what I should do next? Yeah. Yeah, so square both sides. So I'll do that, and I'll do a little bit more. I'm going to square both sides and expand out these quadratic terms here. And if you do that, you get this pretty long, ugly expression, but we'll get something nice and simple eventually. One thing I'd like to point out here is that we do have terms that are kind of quadratic in x on both sides. So we've got an x1 squared and an x2 squared, but we've also got an x1 squared over here and an x2 squared over here. So I can go ahead and kill all these terms. All the sort of second order x terms drop out. In my next step, I'm going to move all of my x2 terms to the left-hand side. So I've got x2 times some number depending on the centroids. And all my x1 terms I'm going to pull to the right-hand side. So I've got x1 times some numbers, and then I've also got some additional terms coming from the centroids over here. Okay, and then for my last step, I'm just going to solve for x2, so I can divide by this constant everywhere. And I get an equation that says that x2 has to be equal to this term in parentheses, it's just some number, times x1, plus this last term, which is again just some kind of number. Here I'm assuming mu sub 2, 2 is different from mu sub 1, 2. It's a detail, don't worry too much about it. But what this means is that the distance between x and the first centroid is the same as the distance between x and the second centroid only if the coordinates of x satisfy this equation. So x2 is some constant times x1 plus another constant. This is exactly a linear equation, right? It's x2 equals slope times x1 plus bias. And so this dashed line here, the equation for this is exactly the equation we derived up here. And so this is a short little proof, just demonstrating that these decision boundaries actually are linear. And in fact, you can solve for them in this nice closed form way for this very simple classifier. Later on, we'll see classifiers that are much more complicated than nearest centroids, and in general, you can't write down nice equations like this for the decision boundaries, but it's a nice demonstration that you can do it here in this case. Okay, I'd like to point out a few sort of limitations of this nearest centroid classifier now. Let's say we have this data set. It's not a real data set, it's some synthetic, made-up data. It's called the 2 moons data set. It's got two features, feature 1 and feature 2, and it's a binary classification problem. So you've got a blue class and a red class. And the thing to notice here is that this data set is not linearly separable. So no matter where I draw sort of a line as my decision boundary in this data set, I'm not going to do a good job at separating these classes. So for example, if I fit a nearest centroid classifier on this data set, I get a centroid up here for the blue points and a centroid down here for the red points. And then my decision boundary, you can see, just isn't kind of complex enough to actually capture my data. And so the nearest centroid classifier is really only good for data that's already linearly separable. You could imagine here somehow drawing a decision boundary corresponding to a more complex classifier that is actually able to separate these two sort of clusters. For another limitation of the nearest centroid classifier is that even if your data is linearly separable, if it requires kind of two lines, then your nearest centroid algorithm still isn't going to do the right thing. So in this case, there's really two separate decision regions for the blue class. Ideally, we'd like to have this be for the blue class, this region for the red class, and this region for the blue class. But our nearest centroid classifier really can only make one decision region per class. So again, another limitation of this very simple classifier. So to summarize our nearest centroid algorithm, the strengths of this model are that it's very easy to implement in code, and it's fairly interpretable and easy to explain. And another sort of major strength of this algorithm is that it doesn't need a lot of data. So even with a small amount of data, you can actually fit these nearest centroid classifiers pretty well. But of course, the main weakness, as I just demonstrated to you guys, is that it's really too simple of a model for most data sets of interest. And in fact, this is kind of a phenomenon of underfitting. So the model is just too simple to match the complexity of the data. Okay, so any questions on nearest centroid classifiers before we move on to classifier evaluation? Okay, cool. So on Friday's lecture, we talked a little bit about classifier evaluation. So we'll do a brief review of what we talked about, and then I'll introduce some more kind of sophisticated methods for evaluating classifiers. So again, you should think of a classifier as some kind of mapping between input feature vectors, like an MNIST digit, and some kind of output corresponding to a predicted label, which will denote y hat. The simplest way of measuring how well your classifier is doing is through its accuracy, where we're just comparing the predicted labels, y hat, to the true labels y. And if we add up sort of all of those predictions, i.e. 1 if it's correct, 0 if it's not correct, and then average them over the testing data set, we get the accuracy of our classifier. So you guys saw these slides on Friday, so I'm going through them a little quickly here. Again, a simple example of how you compute the accuracy is just comparing the model predictions to the true labels, essentially counting up what fraction of predictions the model made correctly. And again, the error rate is something you'll hear me say pretty often. It's just 1 minus the accuracy. Okay. Oftentimes, computing just the accuracy of my classifier is kind of too simple of a method for really assessing how my model is doing. So I'm going to introduce a new concept here called a confusion matrix. And the idea of a confusion matrix is as follows. What we're going to do is, let's say we've trained a model, fit it on our training data, then we went ahead and make predictions on all, say, n examples in some testing set. So this could be a validation set, it could be like a true testing set, some held out data. In a confusion matrix, it's going to be a square matrix with C rows and C columns, where every row corresponds to the true class labels and every column corresponds to the predicted class labels. Then in this matrix, in the row R and column C, we're going to count up the number of times that in our data set the true class was R and the predicted class was C. So we'll see an example of this in a second to make it a little more concrete. In practice, to actually compute one of these confusion matrices, what you'll need is a list of pairs, essentially corresponding to the true class and the predicted class. So we take our classifier, make predictions on a test set, and get these predicted labels. We compare them to the true class. We then initialize our confusion matrix, again this square C by C box of numbers, to be all zeros. Then we just loop through the list and essentially count up the number of entries in row R and column C. So we'll see an example of this again in a second. But one thing I'll point out here is that in homework 2, you'll actually be implementing some code to compute a confusion matrix. So this slide here will be pretty useful for you when you go ahead and attempt that problem. Okay, let's look at an example now. So let's say we have 3 classes in our data set. This could be maybe a penguin data set, for example. And let's say we've got a small testing set of however many rows I have here. What I have listed here is a list of tuples corresponding to a true label and the predicted label. So for this first instance, the true label in my data set was 1, and my model predicted that it should also have a label of 1. For the second one, the true label was 2, but the predicted label was 1, so on and so forth. To compute a confusion matrix then, I just kind of collect all these numbers and summarize them into a table that has 3 rows and 3 columns. So for instance, this number in the top left is the number of times in my testing set that the predicted label was 1 and the true label was 1. This means my model made 2 correct predictions when the true label was 1. For example, this 1 down here means that there was 1 time in this data set where the predicted label was a 1, but my model predicted 1 and the true label was a 3. So yeah, this is an illustration of how you fill out these confusion matrices. And we'll see an example in a little bit of a confusion matrix on an MNIST data set, and it'll hopefully illustrate why we would actually want to compute these in the first place. For now, take me at my word that this is a useful thing to do. I'll point out that accuracy, which is the metric we have been looking at, and these confusion matrices are pretty closely related to one another. So if we denote by n the sum of all the total counts in a confusion matrix, the accuracy of our model then we can read out of a confusion matrix by summing up all the elements on the diagonal and just dividing by the total number of entries in this confusion matrix. And again, this should kind of make sense because the elements on the diagonal are particularly the data points where the model makes correct predictions. Everything off the diagonal represents data points where my model is making a mistake. So of course we can read off the accuracy by doing this procedure here. The error then is also something we can read off of the confusion matrix. It's the sum of the off-diagonal counts because again these are data points where the model is making errors, and we can divide by the total number of points in our data matrix. So for example, using that confusion matrix from the previous slide, if we sum up the diagonal, we get 8 correct predictions. If we sum up all the numbers in this table, we'll see there's a total of 11 predictions. And so the accuracy here is something like 73%. And the error rate, of course, is then 3 over 11. It's this one plus this one plus this one. We get an error rate of about 27%. So let's look at an example of a real confusion matrix. So this is for the nearest centroid classifier. And this is on this MNIST data set that I had shown you guys before. And again, in row I, column J, is the number of test examples with true label I, but predicted label J. So you can see that most of these counts are on the diagonal, which is good, because again, counts on the diagonal represent correct predictions for my model. And off-diagonal cells are representing errors that the model is making. And this is useful for sort of model diagnostics, because we can go in and see what classes my model is confusing with other classes. So for example, this 60 here represents that there were 60 images in my MNIST test set where the model predicted a 4, but the true label was a 9. And this should make a little bit of intuitive sense, I think. It's kind of easy to mix up a 9 and a 4. They look like similar digits. So this might indicate that if we want to make our model better, we can go out and collect more data, particularly from the class 9. So if I can get people to go out and write a bunch of 9s, add those to my data set, it could potentially improve the performance of my model. In contrast, maybe looking at this 1 here, corresponding to when the model predicts a 0 when the true label is 4, it's pretty unlikely that my model makes this kind of mistake. And so it might not be worth my effort to go out and collect more 4s from my data set. So again, the idea of a confusion matrix is it gives us a really fine-grained look at the errors that my model is making. Compare this with accuracy, which is kind of just a high-level single number that tells us overall how good our model is doing. In the special case of binary classification, when we have only 2 labels in our data set, there's some additional terminology attached with confusion matrices. Oftentimes in binary classification, we'll set our problem up so that the label y = 0 is something like the negative class in my problem, and y = 1 corresponds to sort of the positive class in my problem. So for example, in like a medical diagnostic task, y = 0 might indicate that a patient does not have a disease, and y = 1 indicates that a patient does have some kind of disease. If we write down the confusion matrix for a binary classification problem, we can give names to each of these 4 cells here. So in the top left, we'll call this the true negatives. This is when the true label is 0, and the model also correctly predicts 0. So it's the number of times that the model makes a correct prediction for my negative class. False positives, then, are when the true label is 0, coming from the negative class, and the predicted label is 1, coming from the positive class. And then the same idea for false negatives and true positives. But using these numbers, we can compute some more interesting things about our classifier. And people often like to sort of report these interesting numbers to get, again, better diagnostics about how our model is doing. So one thing that people like to compute for classifiers is called the recall of my classifier. And this recall is the ratio between the true positives divided by the true positives plus the false negatives. So we take this cell here, and we divide it by the total of entries in this row here. And really what this is computing is, of all my data points, having true label y = 1, which exactly corresponds to the sum in this row, how many do we correctly classify? We might care about this number because it tells us something like the following. If a patient has a disease, i.e. the true label is 1, how good are we at detecting that disease? How good are we at recalling the people who actually come from the true class? And following our medical diagnostic example, this is a good number to know about, because it essentially tells us if we're actually picking up on the people who have that disease. Another thing we can compute is called the precision. This is the ratio between the number of true positives and the sum of the true positives plus the false positives. So rather than summing up this row for the denominator, we sum up this column for the denominator. And what this precision is telling us is something slightly different. It says, of all my data points with predicted label y hat = 1, which is, i.e., the true positives plus the false positives, the sum of this column, how many do we correctly classify? In other words, if we predict that a patient has a disease, how likely are we to actually be correct? This is telling us, something quite different from this recall. So oftentimes people will report both precisions and recalls for their classifiers, just to get you a better sense of how our model is doing. Okay, so for a simple example, just with some numbers here, our predicted labels here's some numbers for our confusion matrix. The accuracy, again, is the sum of the diagonal elements divided by the total number of elements in this confusion matrix. So we get an accuracy of like 79%. Our recall is 18 over 18 plus 16, so we sum this row for the denominator. And our recall is pretty similar to our accuracy. So, we're maybe not doing particularly good at finding the patients who have a disease. However, our precision, which is 18 over 18 plus 2, so the denominator is summing this column, it's pretty good. We have like a 90% precision. And what this means is that for our model, every time that we predict a patient has a disease, we're very likely to be correct. In other words, we can kind of trust the model's predictions because it has a high precision. Okay, any questions on evaluating classifiers? Okay, no questions? we can go on to the last part of today's lecture, which is all about this k-nearest neighbors algorithm. So, as I mentioned, our nearest centroids classifier is kind of too simple for most data sets. And so here we're going to introduce a new algorithm called the k-nearest neighbors algorithm, which is a classifier that, actually gets used in practice sometimes. So to sort of motivate where this k-nearest neighbors algorithm comes from, we could imagine extending the nearest centroid classifier. So again, in a nearest centroid classifier, we kind of represent each class with its centroid, kind of a template for that class. And one idea to extend this notion is that rather than sort of representing a class by a single data point, our classes can now be represented by sort of multiple different data points. And then a new data point to actually make a prediction for it, to make a classification, we just find the point closest to it in the training data and use that as a sort of way of making classifications. So we'll see an example of this in a second. So given some training data, X, our feature vectors, this is our data matrix, and some class labels Y, this single nearest neighbor algorithm to make a prediction with this method on some new unlabeled feature vector X, what we'll do is we're going to find the feature vector X sub I in our data set that's closest to this new unlabeled data point. So we're just finding the training data point closest to our new testing data point. And to make a prediction for this new data point, we just use the class label Y sub I corresponding to this closest feature vector X sub I. This is another pretty simple and sort of geometric idea where we're just, again, finding the nearest neighbor to our new testing point in the training data. And this is kind of a memorization-based approach. There's no real sort of learning going on in this algorithm. We're just kind of looking up in our data set which data point is closest. Okay, so let's illustrate how this works. Let's say we've got a really simple data set here with 2 features and 2 classes. We've got some new data point X that we'd like to make a prediction for. We can compute the distance to all of its neighbors. So I haven't drawn all the arrows here, but we should be computing the distance between X and every single data point in our training data. Then we're going to pick the closest neighbor and use its label for the prediction. So in this case, this red point is closest to X, and so we would predict red for this data point X. And that's all there is to the nearest neighbors classifier. In kNN, if we draw the decision boundaries, they're again piecewise linear, except they're much more complex than the piecewise linear boundaries we get with the nearest centroids algorithm. So if we had a centroid algorithm, this kind of number of linear pieces in your decision boundaries is equal to the number of classes you have. So here we would only have a single line for the nearest centroid classifier, whereas for kNN we get this, much more complex decision boundary. So what I showed you here is called the single nearest neighbor classification. We just look up the nearest data point in our training data to our testing point. But you can extend this idea a little bit in order to get sort of a more robust classifier. So for k-nearest neighbors, we do something really similar, where for an unlabeled data point X, to make a prediction, we find not just the single closest point in our training data, but the k closest points, where k is some hyperparameter of our algorithm. It's some integer 1, 2, so on and so forth. We then take the labels of these k points that we found to be closest to the training data X, and we just predict the label for X corresponding to the majority of these k closest points. So for example, if our k nearest neighbors had labels 1, 3, 3, 1, 3, the majority label here is 3. It appears most often, and so we'll predict a 3 for this new data point X. That single nearest neighbor algorithm that I demonstrated before is a special case here where we just choose k equals 1. We just look at the closest neighbor. Okay, so here I've got another simple data set, binary classification. Let's say I have a new training point X that comes along. If k is equal to 1, what I do is I look up the nearest data point in my training set to this new point X. It's a blue point, and so I'll predict blue for this data point X. If I increase k to 3 now, the 3 closest data points to X are this blue dot, this red dot, and this red dot. And since there's more red dots in the neighbors than blue dots, I'm going to predict red. If I increase k equals 5, I'll also predict red, just counting up the number of red labels here. So the idea here is that, again, we can just kind of look locally near data point x and see what labels its neighbors have, and use those labels to inform our prediction. Okay, so here I told you that we're going to pick the nearest neighbors, but how do we actually measure this distance or closeness to our neighbors? By default, most people are going to use the Euclidean distance here, which is what we've generally been working with. But sort of in principle, you can use any kind of distance metric here. So you can use like these LP distances that I had introduced before. And oftentimes it takes a little bit of experimentation to determine which distance actually works best for your data set. If you have some kind of domain knowledge about your data set, there might be distances that make a lot more sense than Euclidean distance here. So if your feature vectors are strings, maybe strings of text, you could use something like the edit distance, which essentially counts how many characters are different between my two strings. So this is a different notion than Euclidean distance. Like, how would we possibly even compute the distance between two sentences? It doesn't really make sense. So something like edit distance here might be appropriate for kNN. Another caveat of the kNN method is that it's possible to run into ties pretty often with this method. And what I mean by ties are really there's kind of 2 points, or 2 types of ties. The first is that these sort of type 1 ties, where 2 or more points are equidistant from x. This means x is lying on a decision boundary, and this happens in the nearest centroid classifier as well. This type of tie is pretty rare, but a fairly common type of tie is that after we find the k nearest neighbors and find their k labels, there's no sort of winner, i.e. there's no majority in the label set. So maybe I'm using k equals 2. I look at the 2 closest neighbors. If those neighbors have labels red and blue, well, which should I predict for my data point? There's no clear majority in my neighbor set. In another case, we can just break ties randomly. So we can flip a coin and decide which of these labels to predict. In the case that you have a binary classification problem with just 2 labels, you can always avoid ties of the second type by using odd number choices for your value of k. So yeah, anytime you have an odd number of neighbors, it's not possible to get a tie here. Okay, so here I've shown you sort of the decision boundaries for kNN, and also you should think of these as sort of, again, they're decision regions. So all the points in this region will get classified as red points, all the points down here will get classified as blue points. If I have a new data set come along, say I've added some red data points down here, I can get much more complex, and in fact disjoint decision regions from my kNN algorithm. So if you remember one of those failure modes I showed you guys about that nearest centroids data set, where it couldn't model kind of, 2 disjoint decision regions, the kNN algorithm can actually fix this quite easily. So we see here, kNN is able to actually correctly classify these red points, as well as these red points. Okay. So let's briefly summarize what we talked about today. Looks like we'll end a little early. So we went over nearest centroid classifiers again. And the idea here is we classify new data by finding its nearest class centroid. These have piecewise linear decision boundaries, and I showed you guys a simple proof of how to actually demonstrate this mathematically. These models are pretty simple to implement, easy enough to explain, but they're fairly limited and can't really model complex decision boundaries. And so near centroid classifiers often underfit to our data sets. They get high error rates. We also looked at a few methods for classifier evaluation. So we looked at accuracy, which is, again, this fairly simple, fairly coarse method for evaluation. We discussed how to compute confusion matrices, which give us a finer-grained look at the errors our model is making. And then lastly, we talked about precision and recall, which are numbers that we can compute from our confusion matrix that give us kind of quantitative measures of model performance. And then lastly, we very briefly introduced this kNN algorithm, where the idea is to classify a new data point by predicting the majority label of the nearest training points in our data set. In the next lecture, we'll be focused a lot more on this kNN algorithm, going through some more of the details there. So thanks, guys. Any questions? Yeah, question. Could you say that one more time? Yeah, so the question is, are precision and recall limited to binary classifiers? And the answer is no, but you need to change how you compute the precision and the recall. So you can compute kind of like a per class precision, where you essentially turn a multi-class classification problem and you think of it like a binary classification problem. So if you have 10 MNIST digits, you could turn that into a binary problem by saying 0 versus not 0. And then you can compute precision and recall in the same way. So yeah, you can do it on multi-class problems too. Cool. Any other questions? Okay, thanks guys.